Hello everyone, I welcome you all to our presentation titled Clerestories for Daylighting Deep in Residential Apartments, a search for window-to-wall ratio for bedrooms for dining illumination. I am Professor Ashik Jwardar, Professor of Environment and Energy, Department of Architecture, BUET, Dhaka, and my colleague, Architect Faria Seraj, Assistant Professor, Department of Architecture, DUET, Gazipur, Dhaka, will present our paper now.
Thanks, Professor Jwardar. From the title, it is clear that this research is related to residential apartments of Dhaka, which is the capital of Bangladesh and biggest metropolitan city of the country. So before I start the technical part, I would like to share a quick story of how the urban house forms were generated. From the history, in the pre-Mughal period, courtyards or uthans were found as an inseparable and essential element of both rural and urban houses in Bangladesh. It accommodates the maximum daily activities of the occupants. Because of the changes in the family structure, land ownership pattern, and rapid urbanization, people prefer compact living than the spacious living. As the result, walk-up and high-rise residential apartments become very much popular. In urban residential apartments, traditional courtyard is manifested as the dining space in a consolidated form. As a result, it became a linking space and the deepest part of the residence. To provide daylight in the dining became a real challenge. The aim of the research is to identify the most feasible configuration of clerestory in inner partition walls around dining space with appropriate window-to-wall ratio of the adjacent bedrooms to increase the amount of daylight in dining space under tropical sky conditions. Now I would like to describe the methodology briefly. At first, literature survey was conducted to take decisions regarding daylight simulation. Then the dynamic daylight simulation was done to identify the best possible clerestory configuration for partition walls and window-to-wall ratios of bedrooms. Rating system is developed and metrics are compared. Finally, architectural design guidelines are given to improve the daylight condition of the dining space. This is the plan of the case apartment. The dining space is located at the center of the apartment with no openings for daylighting. Average window-to-wall ratio of the bedroom is 19%. Now I am going to present the simulation method. 3D model of the case space is constructed using Ecotect. Then it is exported to radiance-based simulation tool DESIM. Simulations are performed to calculate the dynamic metrics of the case space on an hourly basis using an annual climate file. Then the comparison and rating are done to find the result and give recommendations. Now the performance evaluation. The entire floor of the dining space and adjacent bedrooms are divided into 0.5 meter by 0.5 meter grids. 6 intersection points on the top of the dining table and 16 points that run through the bed heads of the 2 bedrooms are selected as core sensor points. These are the simulation parameters. The design illuminance is considered as 150 lux for dining space on tabletop and bedrooms at the bed head on analysis grid at 0.75 meter from the finished floor level. The width of the shading device is considered as 500 mm. To evaluate the performance of clerestories, two types of clerestory window configuration, CS1 that is only over the door and CS2 is maximum possible length of the peripheral wall of the dining are placed alternatively on the partition walls around dining space after placing most visible full-height corner windows on the north and south facades. Simulations are performed to calculate the dynamic daylight performance metrics, and the values of the studied metrics indicate that the width of clerestory has a significant effect on the daylighting of the dining space. Clerestory with greater width, that is CS2, can effectively produce a large amount of daylight into the dining space compared to CS1. It increases the daylight autonomy and continuous daylight autonomy of the dining space by 11.5% and 7.61% respectively than the previous condition. Then, 8 window-to-wall ratios starting from 20% to 90% are placed on the bedroom's facade along with most visible clerestory CS2. Simulations are performed in 2 stages. At first, the impact of different window-to-wall ratios of bedrooms on the dining illumination are investigated along with the best possible clerestory configuration. In the second phase, their impact on the bedrooms are investigated. These are the performance of both dining space and bedrooms of the case apartment based on UDI, that is Useful Daylight Illuminance Matrix. In this study, UDI scheme is used to compare the dynamic matrix. As domestic tasks are less desk and screen oriented, so higher upper threshold for UDI achieved can be recommended. Rating points are considered as 7 point to 0 point to suggest the configuration from 1st to 8th place. Rating points of both bedrooms and dining space are plotted in a graph to find the optimum window-to-wall ratio. From the line graph, it is clear that in case of UDI of dining, rating points are increased with an increase in window sizes in the bedrooms, but rating points do not increase gradually with the increase in window sizes in case of UDI of bedrooms because of overlight and glare issues. 40% window-to-wall ratio along with Clerestories CS2 is found to be the most balanced window-to-wall ratio to incorporate daylight in the dining space considering overlight and glare in bedrooms. It increases the value of UDI 100 to 2000 to 60.8% to the core sensor points of the dining space without creating glare in bedrooms. These are the recommendations regarding clerestory and window-to-wall ratio of bedrooms. Clerestories along the maximum possible lengths of the internal partition walls can effectively produce large amount of daylight into dining. 40% window-to-wall ratio is the most balanced window-to-wall ratio to incorporate daylight in the dining space through the adjacent bedrooms with optimized glare and overlight in the bedrooms. The distribution of daylight both in bedrooms and dining space is also improved. These figures compare the UDI 100 to 2000 distribution in both dining space and bedrooms after placing clerestories on the partition walls and optimum window-to-wall ratio of 40% on the bedroom's facade. In the context of Dhaka, occupants spend more time in the dining space during daytime for various activities while the bedrooms are left unoccupied and could be used as a channel for daylight deep in the residential apartment. Operable internal blinds can be used for the windows of the bedrooms in case of overlight and glare. Now, I am at the end of my presentation. To conclude, I would like to say that this paper demonstrates how the internally reflected components can be a source of daylight in the deepest part of urban residential apartments. It also proves that configuration of partition walls and window sizes of the adjacent bedrooms have important effect on the daylighting of the dining spaces. I expect that this paper can be used as a basis for further research to investigate other aspects of daylight inclusion. Thank you. For any question or feedback, please contact with me to fariha.siraj@gmail.com.